So welcome back to my lectures on groups, rings and fields. Our next topic is cosets. Our next topic is cosets. Cosets are basically the subset of a group, a special subset of a group based on a subgroup. And it's been used heavily in factor groups. They are the building blocks of factor groups. So let us see what is meant by cosets. Our idea is to take a group, let G be a group, and H is a subgroup of G. Then we are actually going to divide G into some equivalence classes based on the subgroup. And those classes are actually cosets. So that equivalence class will divide G into disjoint subsets or classes. Actually, there are, in a general situation, if you take any group, abelian or non-abelian groups, going to define two types of equivalence classes. Actually, it behaves almost same, but they are different. So the first one I am going to define is tilde L. Okay, is a relation on G, defined as follows. So what you do is take two elements from here and impose a condition, and if that condition is true with respect to those two elements, then they are related. So A is related to B if A inverse B belongs to H. Going to define the other one also. The right relation is a relation on G defined as follows. A is right related to B if A B inverse belongs to H. Well, when H is an abelian group, these two relations are the same. But we are assuming that it's not necessarily a abelian group. Let us take an example here to clarify this. Let's just take G is equal to C, and H is equal to any subgroup of Z is of the form NC. So let us take 3Z is a subgroup of G, and that is equal to C. So what is C? Is equal to 0, 1, 2, 3, dash, 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 minus 1, minus 2. And 3C is equal to 0, 3, 6, 9, dash, dash, minus 3, minus 6. So let us take two elements, whether they are related or not. So let us take 1 and 2. So you take elements from Z. So let us take 1 and 2. See whether these are related. Let us check for, see this is an abelian group, so we don't need to do both. We can take one of them. If A inverse B belongs to H, then A is related to B. A inverse, what is inverse of 1 minus 1? And that operated by B. So here the binary operation is 2 and that is equal to 1. But 1 does not belong to H. And that means 1 is not left related to 2. Let us take another example. 1 and 4. What is this? This is actually minus 1 plus 4 and that is equal to 3, and that definitely belongs to H, and hence 1 is left related to 4. So basically what is happening here is any element within 3Z are related to each other. Let us say take any two elements from C, 3Z. So that means 3 and 6. They are related because minus 3 plus 6 is equal to 3 and that belongs to H. So if you take any two elements from 3Z, they are related. So that is one's class. So first I am going to prove that this relation is a equivalence relation. So once it's an equivalence relation, it is going to divide G into disjoint subsets. So one of those subsets is 3Z. Now let us take something outside 3Z. Let us take 2 or 1. Let's take 1. 1 is not in 3Z. So what are the elements related to 1? That is going to be 1, 4, 7, 10, etc. Here it is minus 2, minus 5, etc. Because if you take any two elements from here, like let's say you want to verify minus 2 and 7 are related. Yes, it is related because the inverse of this is plus 2, plus 7 is 9 and that belongs to H. So this is actually all the elements in G which is added by 1, actually 1 plus 3C. And of course the next one will be 2 plus 3C. And that's all, because this is going to cover the whole of 3C, the whole of Z. This 3C is this, 1 plus 3C is this, and 2 plus 3C will be 2, 5, 8, 11. This is going to be minus 1, minus 4, etc. So when you combine all these three, it is going to be the whole of 3C. And that is how we are going to divide 3C. Let us first prove that this is an equivalence relation. So this is an equivalence relation. It is reflexive because A is left related to A, and that is because A inverse A, that is equal to E, belongs to H. Now, it is symmetric because A left inverse B implies A inverse B belongs to H. Because this is an element in H and H is a subgroup, this inverse belongs to H, and that implies A inverse B inverse belongs to H, and that implies B inverse A belongs to H, and that implies B is related to A. It is also transitive because A related to B and B related to C implies A inverse B belongs to H and B inverse C belongs to H. Both are elements from H, and that implies the product also belongs to H, and that means A inverse C belongs to H, and that implies A is related to C. So this is really a equivalence relation, and similarly the right relation is also an equivalence relation, and this relation divides G into disjoint subgroups or disjoint classes, and they are called cosets. So the cosets of H under G are 3Z, 1 plus 3Z, and 2 plus 3Z. So these are the cosets of 3C under Z. So So let us write that formal definition of a coset. Let G be a group and H is a subgroup of G. Define the following relations in G. Left relation A comma B belongs to G, then A is left related to B if A inverse B belongs to H. Right relation A comma B in G, then A is right related to B if AB inverse belongs to H. Then left relation and right relation are equivalence relation. These equivalence relation divides G into disjoint classes, subsets left or right cosets. Example, G is equal to 3, G is equal to Z and H is equal to 3Z, then left and right cosets are three Z, 1 plus 3Z, two plus 3Z, and 3Z, 3Z plus 1, 3Z plus 2. See, these are right cosets and these are left cosets, but both are same because Z is a abelian group. Now let us compute the cosets of a non-abelian group. The non-abelian group I am going to take is the dihedral group, which we already discussed in permutations. So these are the rotations and these are the images. This is diagonal image and this is the sidewise images. So this is the multiplication table for D4. So sigma 0 mu 2 is a subgroup of D4 because mu 2 square, mu 2 times mu 2 is 0, identity. Sigma 0 is the identity, so this is a subgroup. So our H is sigma 0 mu 2 and our G is D4. And D4 contains sigma 0, sigma 1, sigma 2, sigma 3, mu 1, mu 2, mu delta 1 and delta 2. 8 elements. So one of the cosets is H. So we are going to define both left and right cosets. Well, I will do the left cosets and I'll leave it to you for verification of right cosets. So one of the coset is H. The other cosets you can get it from taking the element from outside and composing with this. So another one will be sigma, so this is actually equal to sigma 0 mu 2. That is same as the subgroup. So the next one is going to be sigma 1 plus or sigma 1 of, okay, let us make it as plus H. And that is what? That is actually sigma 1 of operated on sigma of sigma 0 and sigma 1 of mu 2. And that is equal to, this is actually sigma 1 and sigma 1 mu 2. Sigma 1 mu 2 is delta 2. So we have taken this one and this one for the subgroup, and sigma 1 and delta 2, sigma 1 and delta 2 is also taken. So let us take delta sigma 2. So sigma 2 plus H is equal to sigma 2 after sigma 0, sigma 2 after mu 2. And that is equal to sigma 2, comma, sigma 2 after M2. Sigma 2 after M2 is mu 1. Next one will be sigma 3 plus h, and that is sigma, sorry, this is sigma 2. Sigma 3 after sigma 0, sigma 3 after mu 2, and that is equal to sigma 3 after mu 2. Sigma 3 mu 2 delta 1. And of course the other thing will be sigma, yeah. So that's all. You covered everything, because you have h, sigma 1 plus h, sigma 2 plus h, sigma 3 plus h. These are the cosets. Okay. So the cosets of the cosets of h is equal to sigma 0 mu 2 under d4 or sigma 0 comma mu 2, then sigma 1 comma delta 2, then sigma 2 comma mu 1, then sigma 3 comma delta 1. See, I am going to leave the computation of right cosets to you, but I just want to make sure that the left cosets and right cosets are not going to be same here, because this is a non-abelian group. Just for an example, let us compute h plus sigma 1. This is sigma 1 plus h. There I am going to compute h plus sigma 1. This here, sigma 1 plus h is sigma 1 comma delta 2. But this is going to be sigma 0 after sigma 1, then mu 2 after sigma 1. And that is equal to sigma 1 comma mu 2 after sigma 1. It is delta 1. See here, sigma 1 plus h is sigma 1 comma delta 2. Here h plus sigma 1 is sigma 1 plus sigma 1 comma delta 1. So right and left cosets need not match. Especially when it is an abelian group, it won't match. And that's what I want to show you. Another alternative definition for coset is this. Our left coset is defined like this. A is left related to B if A inverse B belongs to H. What does this mean? This means that there exists an H belongs to H such that A inverse B equal to H, or you can say B is equal to AH. So if B belongs to AH, then that AH is the coset. So the alternate definition is, let H be a subgroup of G and A belongs to G. Then the left coset of H under G containing A is the subset AH where H belongs to H. So this is a coset. We'll take an example here. Let us take the same example as Z and 3Z. Z and 3Z. So let us take A is equal to 2. Here what I am saying is the collection of elements from Z such that 2 times elements from 3Z. Elements from 3Z, or you can say H such that H belongs to 3Z. This is actually the binary operation plus in Z. So this is actually going to be 2 plus 0, 2 plus 3, 2 plus 6, comma dash dash, and here you will have the negatives also. 2 plus, 2 plus minus 3. So this is going to be 2, 5, 8, etc. Here it will be minus 1, minus 4. So this is our coset as 2 plus 3C. And that's what we found in the last session. So this is sentence. So this is a coset containing 2. You have 2 here. And 2 plus 3C and 5 plus 3C are same because 2 and 5 are related. Here all these elements are related to each other using the left or right relations. So if you take any element from here, you can, then the cosets containing that elements are same. And we can say these are the representatives of the coset. You can take any of them. Minus 4 plus 3C. These are all same. Like that, 1 plus 3Z, 4 plus 3Z, 7 plus 3Z, these are all same. Because 1, 4, 7 are all in that coset and they are all related to each other. And these are representatives of that coset. A very quick result, but it's very important result. Every coset, whether it is left or right, of a subgroup H of G has same number of elements. So what we are going to do is we are going to define a bijective map from H to one of its coset. So define a map, let's say phi from H to AH. For right coset, it will be HA. This is the left coset. Then, they defined by as follows. Phi of H is equal to AH. So, phi is onto. Why? Because for every H, that is how it is defined. Onto because phi of H is equal to AH. In other words, you can say, so what you can do is, we can prove this. Because, so what you can do is, let B belongs to AH. And that implies there exists an H in H such that B is equal to AH. And that implies phi of H is equal to AH is equal to B. So phi is onto. And phi is 1, 1 because phi of H1 is equal to phi of H2 implies AH1 is equal to AH2, and these two are in a group, so left cancellation implies H1 is equal to H2. That implies phi is a bijective map, and that implies H and AH contains same number of elements. Next we'll do an important theorem, the theorem of Lagrange. Let H be a subgroup of a finite group G, then the order of H divides order of G. This is actually very straightforward from the previous result. So let G contains n elements and H contains m elements. And from the previous result, every coset of H under G contains same m number of elements. And suppose there are such cosets, then n is equal to mr. Because each coset has got the same number of elements as in H, and that implies m divides n. And that's what we want to prove. M is the order of the subgroup, n is the order of the group. we will derive a very simple result on finite groups. Every finite group of prime order is cyclic. So we are going to use the theorem of Lagrange here. So let G be a group and its order is equal to P, where P is a prime number. Then A different from, then let A different from E belongs to G. Then the subgroup generated by A is this is a subgroup of G. So using theorem of Lagrange, the order of the subgroup generated by A must divide the order of G. But order of G is prime. That implies G is equal to, because A is different from E also. And that implies G is cyclic. Now we'll do a simple definition here. Definition. Let H be a subgroup of a finite group G, then the number of cosets of H under G is called the index and is denoted by G colon H. Now there is a very simple result. Let G be a finite group and H and K are subgroups of G such that H is a subgroup of K is a subgroup of G. Then the index of G over H is equal to the index of G over K times index of K over H. So it is very simple because, so let order of G is equal to N, order of K is equal to M, and order of H is equal to L. So what does this mean? So this means M is equal to L times R, where R is the number of cosets of H in K, and N is equal to M times S, where here R is R, so where S is the number of cosets of K in. So that means N is equal to that means N is equal to okay, then that means N is equal to LR times S, and M is equal to T times L, where T is the number of cosets of H in. So this is actually N. N is equal to TL, where T is the number of cosets in. So from these two equations we can say that L is equal to R is equal to T is equal to RS. Both are N. So T is equal to RS from 1 and 2. And what is R? R is the number of cosets H in K. So this is actually, what is T? T is actually number of cosets of H in G. So this is actually G over H is equal to R is K over H, and S is G over K. And that's what we want to prove. We'll do a couple of problems before we close this chapter on cosets. The first problem we are going to do is find the index of the subgroup generated by 3 in C24. So what is C24? C24 is equal to 0, 1, dash, dash, 23. Or you can say the order of 24 is equal to 24. What is the subgroup generated by 3? 0, 3, 6, 9, 12, 15, 18, 21, and that's it. And that is 1, 2, 3, 4, 5, 6, 7, 8. Or we'll say that implies 3 is equal to 8. So the index of C24 over the subgroup generated by 3 is equal to 24 by 8, and that is equal to. We'll do our last problem in this session. That is, let H be a subgroup of G such that G inverse HG belongs to H for all G in G and H in H. Then show that GH is equal to HG, meaning the left and right cosets are same. So what we do is, we'll take an element from GH. So let A belongs to GH, and that implies there exists an H belongs to H such that A is equal to GH. So that implies this is equal to G inverse G, because this is E. And this belongs to, since G inverse belongs to H, because this belongs to H because of this. This can be written as G inverse of inverse H G inverse. So this is of the same form. So this is actually an element of H. So that means this implies A is equal to H1 G for H1 is equal to G H G inverse. And this implies A belongs to HG. And similarly, we can show that, so this implies GH is a subset of HG. Similarly, HG is a subset of GH, and that implies GH is equal to HG. So this is an important condition for a left coset to be equal to right coset.